The alternating series test for convergence says that if you have a series that meets all three of the following conditions right there, then it must converge. So the first condition is that each u sub n term, or a sub n, or whatever you want to call them, I don't know why I call them u here, but I've been calling them a's. As long as each term is positive, right, and then we have this -1 to the n plus 1 in there that makes it alternate. So as long as it actually alternates from positive to negative, to positive to negative, to positive to negative terms, that's criteria 1. And then criteria 2 would be as long as the term before is always larger than or equal to the next term. Right, so if at some point on here, let's say after u sub 3, the next term is always going to be less than the previous term, that's criteria 2. And criteria 3 says the limit as we approach infinity needs to be 0 of that nth term. And so if those 3 criteria are met, the alternating series will converge. So this is only for an alternating, that's on not the right color or even the right size. Let's try that again. There we go. As long as it's an alternating series, right, as long as the terms get smaller, and as long as the limit as n approaches infinity of the nth term is 0, then we're good. It should converge. It doesn't, I mean, n equals 1 only because this is n plus 1. If this was just -1 to the n, we'd say n equals 0. Just so we started a positive term. Nick. It doesn't really matter. I could put n plus 1001 here if I wanted to, and it's not gonna, it won't affect the series itself. All that -1 to the n plus 1 does is just make it alternate. So. Okay. So moving forward, let's prove that the alternating harmonic series is convergent, but not absolutely convergent. And then we want to find a bound for the truncation error after 99 terms. So first off, what is the alternating harmonic series? It is just the sum from, just because Nick hates it, we'll do n equals 1 to infinity of -1 to the n plus 1 times 1 over n, right? That'd be the alternating harmonic series. Harmonic series is just a series of 1 over n. Alternating, we throw the -1 to the n plus 1 in. So can we prove that this is convergent? Number 1, does it alternate? That's criteria 1. Does this series alternate? Yes, we can see that very obviously because nothing in here is going to change my signs, but this will make the signs flip each time. Without the -1 to the n plus 1, we have all positive terms. The -1 to the n plus 1 makes it alternate. Check. Perfect. All right. As we go from smaller n values to larger n values, do the terms keep getting smaller? Do the absolute values of the terms keep getting smaller? Or do the terms from 1 over n, disregarding the alternating part of it, do they keep getting smaller? Well, the first term here would be a 1, right? The next term is a half, and the next term is a third, and then a fourth, and so on, right? Are those getting smaller? Yes, wonderful. Check, getting smaller. Just like my check marks are getting smaller. Perfect. All right, and then lastly, we want to know, does the limit as n approaches infinity of -1 to the n plus 1 over n, right, times 1 over n, equal 0? -1 to the n plus 1 is just a -1 or a 1, right? And if we're dividing that constant by infinity, what do we get? We should get 0, exactly. So check, it meets all 3 criteria. So we could say that this converges by the alternating series And what would our bound be on our error after 99 terms? Back to our alternating series error bound. What is the alternating series error bound? After in terms, it is the in plus first term. So the term after 1 over 99 ought to be 1 over 100. Everybody good with that? All right, now we wanted to prove that it was convergent but not absolutely convergent, so that means we also need to take a look at the absolute value of that function, or of that series. And what does that absolute value of that series look like? It looks like the sum from n equals 1 to infinity of just 1 over n, right? And we know that that diverges by what test?
P-series.
P-series test. And so we've shown that the alternating harmonic series, -1 to the n plus 1 times 1 over n, converges by the alternating series test, but it is not absolutely convergent. We call that conditionally convergent. So another important term that you will need to know and be able to use. A series is conditionally convergent if it converges, but the absolute value of the series does not converge. Good? Any questions on that? That's our easy start to our day. Then we'll have our fun theoretical continuation for the day, and then we will get into the stuff that's more difficult. Any questions before we move forward to the fun theoretical stuff? Are we allowed to abbreviate the test we use in the AP exam or reiterate the whole test? It's probably better if you write it all the way out. But if you're short on time, if those 7 seconds are going to make or break your exam, then abbreviate it and you'll probably be fine. I mean, I've even seen in their scoring guides where they abbreviate the tests. So it's probably fine, but nowhere does it explicitly say that you don't need to, or that you don't need to write them all the way out. I don't understand your question, Nick, because the absolute value is divergent and the original function is convergent on some interval. There's no function here per se. I mean, this is just a series, right? The functions, we end up with series that represent functions when we throw x's in there. We don't have any x's in there. These are just series of, it's a series of numbers. It's just a sum of a bunch of numbers. It's not convergent on an interval per se. It's just this series is either convergent or it is divergent, because there's no, the intervals pop up when we say, all right, let's throw some x's in here and find the x values for which this does converge. Does that make sense? Is okay a yes or no? Yeah, okay. Okay, perfect. All right. Any other questions before we move on? Okay. Here I have a couple of fun questions for you. Can you rearrange the terms of a finite sum into some other order without affecting the sum itself? So, simplest example of this, right, would be something like 2 plus 3 plus 4 plus 5 plus 6. That equals something. I don't even know what numbers I just said. I think what did I say? 2, 3, 4, 5, and 6. Right? So that equals 20. Can you rearrange all of those terms without changing the sum? Can I add them in a different order? Yes. And why can we do that, Darius? That's so close to being right, Adrian. Not the commutative, but the commutative. Replace that in with a T. No, no, that is even worse. Commutative. There you go. That's the one. Commutative. The third one you wrote there. The commutative property of addition, right? Yeah, we can rearrange them, right? That's no problem. That's right. Third tries charm. Third time's a charm. So yes, we can rearrange the terms of a finite sum without affecting the sum, right? This is the commutative property. And see, if you just have really terrible handwriting, nobody can tell if you're spelling it right or not. Who knows how many M's and U's and N's and whatnot are in there. So yes, the commutative property, right, tells us we can do this. Okay, perfect. Now, what if I have an infinite series that sums up to some value, right? Just like I have the alternating harmonic series, we know it's convergent. So can I take, I don't know, 50 of those terms, let's say, and rearrange them, and will that affect the sum of that series? Or suppose I took 100 of them and rearranged them into a different order. Would that affect the sum? Hopefully not. That's right. It would not. Right? We should be able to do this. Yes, the commutative property. Right? The commutative property tells me I should be able to do this. Take 1,000 of them, rearrange them. Doesn't matter which 1,000. Pick any 1,000 you want, and then sum together all the other terms that are in this infinite series, and you still get the exact same value that you started with. That series should equal. Okay, last question. Can you take and rearrange an infinite number of the terms of an infinite series? So can I rearrange all of the terms in an infinite series without affecting the sum? All right, and so probably yes, I think so. See, now you're all wrong. This is a not necessarily. Not necessarily. And we cannot rearrange an infinite number of the terms of an infinite series without affecting the sum all the time. Sometimes you can, but not always. The subtraction does sort of have something to do with it. So here's what we're going to try to do. We are going to take a look at a series that converges conditionally. And we can take the terms of that conditionally convergent series and rearrange them to form another series that is divergent. So I can actually take the terms of the alternating harmonic series, which we just proved was convergent, and rearrange them all, rearrange 100% of them. No, it doesn't have to be 100% of them, but almost 100% of them. I could rearrange 100% of them to form a divergent series. I could also rearrange them to form a series that converges to any value that I want it to. And so here's how we would do that. Suppose we wanted it to form a divergent series. So what we're going to do is let's first write out just write out the positive terms. This is not the answer, but the positive terms would be a 1, right, and a 1/3, and a 1/5, and a 1/7, and so on, right? All the odd numbers would be our denominators. And then our negative terms would end up as something like we'd have negative a half, right? And we'd have negative a fourth, and we'd have negative a sixth, and so on, right? Negative an eighth, negative a tenth. So, all right, so here's what we're going to do. We are going to make this form a divergent series by, let's see, what do we want to start at? Let's start at 1. Let's keep our first term, and in fact, we're going to keep our second term the same. We're starting at 1. I'm going to subtract a half. All right, after doing that, 1 minus a half. If I took that partial sum, I'd be at a half, wouldn't I? But if I stopped here and took the partial sum of this series, I'd be at a half, wouldn't I?
Yes.
1 minus a half equals a half, right? Unless I've lost my mind. Okay. All right. I'm just going to assume that your silence means yes. Okay. So what's a number that we are now less than? That we are now greater than. No, that's it. I'm saying this right. What's a number that we are now less than, but that we were greater than when we started out? So we're now at a half. What's a number that's greater than half, but less than the one that we started at? 3/4. All right, 3/4 sounds good. So let's say that after these two terms, we are now, I'm going to do this in a different color. We are now less than 3/4. All right, so what I'm going to do is I'm now going to add in some positive terms. And I'm going to add in those positive terms until I have gone back up to be above the value I started at, to be back above 1. So I need to add a third in. So if I'm at a half and I add a third, have I made it back above 1? Not yet, right? I need to add in another fifth. And if I do 1 minus a half plus a third plus a fifth, what's that sum? Something that is greater than something that is greater than, yeah, it's 31/30, right? Which is greater than 1, isn't it? Did you say that we are now greater than 1? Okay. So now what I'm going to do is I'm going to subtract some negative terms until I get back below 3/4. So I'm going to subtract a 4th. And then I'm going to subtract a 6th. Does that get me below 3/4, or do I need to do an 1/8 also? I'm trusting in you guys with the calculators. That's below, perfect, okay. So we are now below, we're now below 3/4. All right, so now what I want to do, any guesses? I'm going to add in a 7th, and I'm going to add in a 9th, and I'm going to add in an 11th, until I get back to something that is greater than 1, right? And then once I get to something that is greater than 1, I'm going to subtract a bunch of terms until I am again less than 3/4. Then I'm going to add in a bunch of terms until I'm greater than 1. And because I have an infinite number of terms to work with, I may have to add in a whole heck of a lot of terms to get back above 1 and back below 3/4 every time. But I should always be able to get above 1, and I should always be able to get back below 3/4, because these terms are terms of a divergent series that will always keep increasing in value. Does everybody see that? So I should always be able to get above 1 and below 3/4. And if I'm always going above 1 and then back below 3/4 and then back above 1 and back below 3/4, is there some specific number that I will be converging to?
No.
No, right? I'm not going to converge to some value. Even though if I put them in descending order by absolute value, I will get a specific value. Right? I will not if I rearrange them in this infinite way where I go above 1, then below 3/4, and above 1 and below 3/4. And obviously I could have picked stuff that's, I could have said I want to go below, 0.99999 and above 1, and then I wouldn't have to use as many terms when the values get a lot smaller. But isn't that crazy that you can take all of the terms of a sum, of an infinite sum, but rearrange them into something that does not have a sum? Wow. It just blows your mind, doesn't it? So, wow, that one down there is really small. Could we rearrange the terms of that same series to form a series that converges to a value of 1? Any thoughts on how we might do that? Nobody? No thoughts on that? Somebody must have a thought. I have an idea. Let's start with 1. What term do you want to put in after 1? Oh yeah, yes, James. The new series will still have an infinite number of terms, most definitely. So what should we put in there after the 1? How about -1/2? Everybody good with that?
Yes.
All right. Well, then what should we do? Let's make it so that it goes back above 1. So if I add a third to that, am I back above 1?
No.
No. What if I add a fifth? Before we said adding a fifth would make us back above 1, right? So this was less than 1. And now we've added in terms to make it greater than 1. And then what do we need to subtract to make it less than 1 again? If I subtract a fourth, am I back less than 1?
Yes.
Should be, right? And what do I need to add to make it greater than 1? If I add a seventh, am I back greater than 1? No. But what if I add a ninth? Am I back greater than 1? Now I don't know. You'll have to tell me. You've got the calculator. How far do I need to go to be back above 1? Those of you with the calculator in front of you. I don't know. Does adding an 11th get me there? Did a 7th and a 9th do it? A ninth is enough. Oh, man. Okay, a ninth did it. Cool. And then what would we do? We'd subtract a sixth. This puts us back greater than 1. And then minus a sixth, I bet that's already going to put us back less than 1. In fact, I'm positive that it will. And then what do we need to do? We need to add in an 11th and a bunch more terms until we are back greater than 1. And then we will do what? Then we'll subtract an 8th. And that'll put us back below 1. And then we'll add some more terms until we are again greater than 1. And then we'll subtract the next value. That'll make us less than 1. And should I be able to do this infinitely forever?
Yes.
I should be able to, and I should be converging to a value of 1 because every time I'm going back and forth oscillating around this value of 1, and I'm getting closer and closer. Every time I flip signs, I'm getting closer and closer and closer to 1. And so it should converge to a value of 1, which is a little bit crazy to think about because what does this series from n equals 1 to infinity actually equal if you do it in order? This is the series for natural log of 1 plus x, effectively. This series should equal natural log of 2. Right? This series equals the natural log of 2 when written out in its regular order from n equals 1 to infinity. But by writing it in a different order, we can make it diverge. We can make it converge to a value of 1. We can make it converge to any value that we want. We can make it converge to 0. We can make it converge to pi. We can make it converge to 1,000. We just got to put a lot of terms in it and add those terms together for a very long time until we get above 1,000, then subtract 1 to get below 1,000, then add a whole heck of a lot of terms to get above 1,000. We can make this series converge to any value we want, even though when we do it in the appropriate order, it converges to an exact value of natural log of 2. So when we get into these ideas of infinite series and infinite sums from infinite series, some of the basic rules of math that you learned way back when you were in elementary school start to fall apart, which is hopefully mind-blowing. Wasn't it? Wasn't that mind-blowing? Aren't you astounded by what you've just done? You've taken a sum and rearranged the terms to get a different value. And you've taken a sum to rearrange the terms and not be able to find a sum. Pretty cool, huh? Wow, yeah. Oh, come on, people were saying things in the chat and I didn't hear you. Yes, natural log of, it's natural log of 1 plus x effectively is what this series is, but we've got a 1 up here, right? It's x to the n over our n value, right? That's what natural log of 1 plus x was. Negative 1 to the n plus 1, x to the n over n. So this is that series with x equal to 1. Does that make sense, Nick? Like if you look back at your series for
yes, that makes sense.
Okay, yeah, it's natural log of 1 plus x. So this is, this is x to the n, but we've plugged in 1 for x, which is what makes it natural log of 1 plus 1 or natural log of 2. And then what did I don't know, somebody else said something. The terms themselves never change. What you mean, like, yeah, we will still use, since we're doing an infinite sum, Adrian, we will still use every single term in here. I mean, obviously we can't sum together the terms infinitely. Like by hand. But yes, we're still using all of the exact same terms. None of the terms themselves change. No, it does not mean that, Adrian. It doesn't mean that, strangely enough. So it's because of the order that we're doing them in that makes it change. I mean, if I were to then rearrange them back into this order, into the original order, sure, yeah, then it becomes natural log of 2. But we are effectively changing the order of them infinitely forever. Well, yeah, see, so Adrian, that's the part where I'm saying that these rules, like the commutative property of addition, it breaks down. It's no longer true when you have an infinite number of terms in an infinite series, that for a series that converges conditionally, because there's there's no way to be done per se. And so the sum of an infinite series is the value for which it is converging towards. And so if we write those terms in their order from n equals 1 to infinity, sure, it converges to natural log of 2. But if we write them in this particular order, following this pattern where we always add terms to get less than 3/4 and then greater than 1, then it diverges. And we just follow this pattern infinitely. And if we follow this pattern infinitely, it will converge to 1. And if we follow the pattern of 1 minus a half minus a fourth plus a third minus a sixth minus an eighth plus a fifth, where we're going around a half, then it goes to half, right? Because you never reach the end of the pattern. That's exactly right. And it goes on infinitely. That's the little caveat here. Where here, can we rearrange an infinite number of the terms of an infinite series, right? So we're taking an infinite number of them, not a finite number of them. If we take a finite number of them, then you can rearrange them however you want, and eventually you'll get back to that same sum. But if we take an infinite number of them and rearrange them, we don't necessarily get that same sum. And this will only work if you have something that converges conditionally, right? Not absolutely. If it converges absolutely, then you can't do this. Does that make sense to everyone or no? I know, it's making that firm grip that you thought you had on reality slip away, right? But math will do that too. All right, let's move forward then to what I really want to do today for our last 30 minutes or so. Hopefully we get through it all. We'll see. We'll see. All right, so what we're going to do is we are going to now fully test different power series for convergence. So what we're going to do is we're going to use a test, generally the ratio test. And then we might end up having to use some of our other tests. We can use a direct comparison or a limit comparison or assorted other tests to figure out when the series converges absolutely. Once we've figured out when a series converges absolutely, so we've gone through and used that test, we are going to then test the endpoints. And we should now have enough other little tests to work on convergence at the endpoints. And so we can determine if the series will converge absolutely or conditionally at the endpoints. And we should then be able to write out a full interval of convergence and a list of when it converges conditionally, when it converges absolutely, and what the radius of convergence itself is. So that's what we're going to be doing. So we're going to do 3 or 4 of these here and see if we can figure out the complete convergence of different power series. So here we have -1 to the n plus 1 times x to the 2n over 2n from n equals 1 to infinity, which looks like x squared over 2 minus x to the 4th over 4 plus x to the 6th over 6, and so on. So first question I will ask you here is, for any x value, is this thing positive? Does this thing have all positive terms? It does. This negative is positive? No. Yes. Yeah. The x squared and the x to the 4th and the x to the 6th and the over 2 and over 4 and over 6 make it all positive, but the -1 to the n plus 1 tells us that we are alternating, which tells us that this series does not have all positive terms. I see what you were saying right there. It's the squared and the 4th and the 6th were all positive. But technically the terms of this series come from all of this, right? And so these negatives make it so that's not the case. So since it's not all positive terms, we're going to have to look at the absolute value of this series. And what does the absolute value of this series look like? Should be this, right? And what does that absolute value effectively do? It gets rid of the -1 to the n plus 1, right? The x to the 2n is now still going to be positive because that's going to give me the even exponents up here. And then divided by 2n will always be positive. So the series we're going to look at to determine our convergence, to determine our absolute convergence, is just going to be the series of x to the 2n over 2n. Good or no? Okay, so then we will use our ratio test. And our ratio test says do what? Look at the limit as n approaches infinity of what? The ratio of the n plus first term to the nth term. So the limit as n approaches infinity of x to the 2, and instead of n, it'll be 2n plus 1. And for some reason, as soon as we start throwing n's in here with series, people start like trying to just write 2n plus 1 here and not 2 times n plus 1 and distributing it out. So just be careful about that because it can affect your radius of convergence. Right, don't just make this 2n plus 1. Make sure it becomes a 2n plus 2 up there. And same thing down here. Don't make this just a 2n plus 1. This is 2 times n plus 1. And then we'll divide that by this x to the 2n over 2n, which means we're going to multiply it by 2n over x to the 2n. Good with that? Okay. And if we simplify this down, this is x to the 2n plus 2 over x to the 2n. What's that going to leave me with? Yep, should be x squared times 2n over 2n plus 2. Since n is our variable, 2n over 2n plus 2 means these both have a degree of 1. Divide the leading coefficients. The leading coefficient of this is 2x squared. Leading coefficient of this is 2. So that gives us a limit of x squared. And using the ratio test, if our limit, x squared, is less than 1, that's when it converges. And so when is x squared less than 1? X squared is less than 1 when x is less than 1 greater than -1, which tells us we have a radius of convergence of 1. Good? So far?
Yes.
Okay. And we know that this series converges absolutely on this interval. Okay? And absolute convergence implies convergence, so we know that it will also just regularly converge on this interval. Now, we have to then move on and start talking about the endpoints. So what endpoint do we want to start with? You guys want to start with 1 or -1?
1.
All right, let's start at 1. Sounds good. Okay, so we will then say at x equals 1, what does our series become? At x equals 1, our series is the sum from n equals 1 to infinity. And remember, we have to go back to the original series, not the absolute value one that we were looking at. This is -1 to the n plus 1, and then it should be 1 for x to the 2n over 2n. And what does that series become? That's just the sum from n equals 1 to infinity of -1 to the n plus 1 over 2n. True?
Yes.
Okay. What can you tell me about that series? Number 1, what type of series is it? -1 to the n plus 1 tells us that this series is alternating, which means we hopefully can use the alternating series test for convergence, right? So number 1, criteria is met. It is alternating. Do the terms get smaller as we go forward? If I plug in 1 here, what do I get? And I'm going to get a half, right? If I plug in 2, I'm going to get a fourth. And then if I plug in 3, I'm going to get a 6. And if I plug in 4, I'm going to get an 8, positive or negative for each of those, right? The terms are decreasing. So criteria 2 has been met. What about criteria 3? What's the limit as n approaches infinity of this?
0.
0. And so we should be able to say all 3 criteria are met. So we should be able to say that this converges by the alternating series test. Okay. What about, though, the absolute value of this? What does this series become? It just becomes 1 over 2n. And what do we know about that series? It diverges by the p-series test, right? So we can say that our actual series converges at x equals 1, but it does not converge absolutely there. It converges conditionally at x equals 1. Okay. Now we have to check our other endpoint. Our other endpoint was at x equals -1, right? So if x is -1, we're looking at the sum from n equals 1 to infinity of -1 to the n plus 1 times -1 to the 2n over 2n. And what does that series become? What's -1 to the 2n?
+1.
It's just +1 no matter what, right? No matter what value for n I put in here, this is always an even exponent, which makes the -1 positive. So we just end up with -1 to the n plus 1 over 2n, which we just dealt with. What do we know about that one? It converges by the alternating series test, right? We just did that. True? And if we think about the absolute value of it, what's going to happen? We're going to end up with effectively what series? Sum from n equals 1 to infinity of 1 over 2n, which we just also said diverges by the p-series test. Everybody agree with that? Cool. So what we will say is, for this series, the radius of convergence is 1. It converges on the closed interval -1 to 1, because that's what we found, that it did converge on -1 and 1. We will want to say that it converges absolutely only on the open interval -1 to 1. And we will say that it converges, and you want to list all of these things, that it converges conditionally at x equals -1 and x equals +1. Everybody good with that? This would be the final answer to that question. Any issues, any problems, any issues with that? Everyone's good? Cool. All right, let's do another one. Let's find the radius of convergence, interval convergence, et cetera, et cetera, et cetera. Oh, wait. Okay, I'm waiting, Nick. What am I waiting for?
So like back to the last one. So because you did the absolute value of it for both x equals 1 and -1, and you found that it diverges, that means that it converges conditionally, right?
Correct. At x equals -1, it converged, but the absolute value did not converge. And the same at x equals 1. At x equals 1, the series converged, but the absolute value of it did not converge. And so that's why I said here at the end that it converges on the closed interval, but only absolutely on the open interval, because we had found from the very beginning, okay, cool, blah, 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 we went through all here, converged absolutely from -1 to 1 open interval. Then we checked the endpoints and said, converged at 1, but not absolutely. Converged at -1, but not absolutely. Therefore, converges closed interval, absolutely, open interval, conditionally at whatever points it converges on, but not converges absolutely.
So if you did the absolute value and you would have found that it also converges, then it would converge absolutely on that closed interval too?
Correct. Yep.
Okay. Okay.
Shayla, did that answer your question also? Okay, perfect. Any other questions on that before we move to the next one? Okay. Let's take a look at this series. For all values of x, is 10x to the n over n factorial positive? No, exactly. Right. If I put a negative value in for x here, we get negative terms. So we're going to say this is not all greater. Well, I'm going to say not all positive terms. Not all positive terms. I'm going to be more specific. So in order to start looking at this using our ratio test, we will need to take the absolute value. Let me see here. Sorry, Delphine had another question here. We use the absolute value to find the radius of convergence. Since why do we list them all? Like, why do we list the absolute convergence and the conditional convergence and just the convergence? Is that what you're asking, Delphine?
Yes, because in the last problem, we since it wasn't all positive terms, we used the absolute value to find that it converges absolutely, which implies convergence.
Mhm.
But then when we went and checked the endpoints, we said that it converges on -1 to 1, including those terms. So why did we list all three of them?
Like why, I mean, you're just saying, why did I list this convergence, and this convergence?
Yeah.
Just that's normally what that's normally what you'll be asked to do for any series, is to say the radius of convergence, the interval of convergence, the interval on which it converges absolutely, and any values at which it converges conditionally. That's just normally what it will ask. So, I mean, that's what we said here, right? It says find the radius of convergence, the interval of convergence, the values for which it converges absolutely, and the values for which it converges conditionally.
Okay, thank you.
It just wants us to list them all. That's normally what the questions will say. Yep. All right, so we said not all positive terms here for this one, which means we're going to take the absolute value of it. So sum from n equals 1 to infinity, absolute value, 10x to the n over n factorial. And so we will then look at the limit using the ratio test. The limit as n approaches infinity of 10x to the n plus 1. Put this all in absolute value, 10x to the n plus 1 over n plus 1 factorial times, and then the reciprocal of this, so n factorial over 10x to the n. And what does that give us? As n approaches infinity, 10x to the n plus 1 over 10x to the n just gives us 10x. And n factorial over n plus 1 factorial gives us what in the denominator? N plus 1, exactly. All right, and what does that limit equal? The 10x is just a number, right? X is just a number. Doesn't matter if it's a million or 10 billion or -7. It's that divided by infinity plus 1. What is a constant divided by infinity? It should be 0. And what does the ratio test tell us if the limit comes out to be 0? Tells us that it converges, right, for all values of x. So we will say this converges, and we can indicate that it is absolute convergence because we took the absolute value. So it converges absolutely for -infinity to infinity with a radius of convergence of infinity. And since it converges absolutely for all real numbers, we could say that it never, there's no conditional convergence, because conditional convergence is only if it converges, but not absolutely, but it converges absolutely for all values. Good or no?
Wait, so how do we get the radius of convergence is infinity?
Say it again.
How do we get the radius of convergence to be infinity?
So the ratio test says that if the limit of this, n plus first term over the nth term is 0, that it converges for all real numbers, for all real x. That's just what the ratio test says. So we're, I don't know if it's in this slide of notes. I don't think it is. I don't think I can go back to it, but that's just the rule for the ratio test. Okay. All right. Everybody good or no? Ready for another one? All right. N factorial times x plus 1 to the n from n equals 0 to infinity. Does this have all positive terms for all real numbers x?
No.
No, not all positive. So we will look at the sum from n equals 0 to infinity of the absolute value of n factorial times x plus 1 to the n, which is what? With our ratio test. Should be the limit as n approaches infinity of n plus 1 factorial times x plus 1 to the n plus 1, put all that inside absolute value, divided by n factorial times x plus 1 to the n. And what do we get if we simplify that? We end up with the limit as n approaches infinity of what? N plus 1 factorial, for n factorial is n plus 1, right? And then what? X plus 1 to the n plus 1 over x plus 1 is x plus 1 to the first. And what does that limit equal? The right answer here is, well, it depends on x. Normally, let's say I chose x equals 1,000. What is this limit? Should be infinity. Exactly. Suppose I chose x equals 0. What's this limit? Should still be infinity. Suppose I chose x equals -7. Then this limit should be negative infinity. That doesn't affect the ratio test. But for what singular specific x value does this limit not equal infinity? Right, at -1. So we will say this equals either positive or negative infinity if x does not equal -1. Because if x equals -1, I have 0 times n plus 1, which is 0. And if I look for the limit as n approaches infinity of 0, that would just be 0. And the ratio test tells us that if you end up with an infinity, or a limit that doesn't exist for your limit in the ratio test, that what is true? That it should diverge. Right? So where does this converge then? We'll say that this converges, and we'll put in our caveat absolutely also, at x equals -1 only. And the radius of convergence is 0. It never converges conditionally. And if we wanted to, we could say that it diverges everywhere but x equals -1, but it didn't ask that. So could say negative infinity to -1, -1 to infinity, but that's not a big deal. It solely converges absolutely at -1. Radius of convergence 0, never converges conditionally. Good or no? All right, last one. So first off, for all x values, for all real x, is this always positive terms? No, not all positive terms, right? Not all positive terms. So we're going to look at the sum from n equals 1 to infinity of the absolute value of x minus 3 to the n over 2n And as we do our limit using the ratio test, we'll look for the limit as n approaches infinity of x minus 3, absolute value of x minus 3 to the n plus 1 over 2 times n plus 1 times the reciprocal of what we started with there, which is 2n over x minus 3 to the 2n. Everybody good with that? No, sorry, I missed your question there, Nick. We know that the convergence is absolute for x equals -1 on the last one because we took the absolute value of this to find that convergence. Okay. All right. Everybody good with our start of the ratio test for this last one here? Good question, Aiden. It's a 2n because I saw all the other 2n's and wrote a 2n. It shouldn't be a 2n. Okay. Let me just rewrite all of that because now that looks like garbage. There we go. Thank you. I don't know. I saw this 2n and just kept writing 2n's. Everybody good with that now? Okay. So as we simplify our terms down, what do we end up with? We end up with a limit as n approaches infinity of the absolute value of, let's see, x minus 3 to the n plus 1 over x minus 3 to the n is just x minus 3. And we can cancel the 2's, I guess, if we want. Just n over n plus 1. And as n goes towards infinity, the n over n plus 1, divide the leading coefficients. That goes away, and you're just left with the absolute value of x minus 3. And we want this to be less than 1, which should be pretty easy to solve. X minus 3 less than 1, greater than -1, gives us x is less than 4, greater than 2. Everybody good with that?
Yes.
All right, so what's our radius of convergence? Our radius of convergence should be our radius of convergence should be 1, right? It's always this value, right? This is our radius of convergence right here. Absolute value x minus a is less than our radius of convergence. So our radius of convergence is 1 because we're going from 3 to 4 and from 3 to 2. Right? And then we should, what do we need to go in and do? We need to check our endpoints, right? So what do we want to check first, 2 or 4?
4.
4? Okay, 4 it is. So let's put in a new page here and say at x equals 4, what does our series become? We had x minus 3, which is just a 1, right? We end up with just 1 to the n over 2n. Where are we starting? We're starting at n equals 1, I bet. And those are all positive, which means I don't need to take the absolute value of it. Right? This will just be absolute convergence and convergence. But what do we get? We get that it diverges by a p-series. And like we said, since this is all positive terms, we don't need to bother to do absolute convergence. What about at x equals 2? At x equals 2, we got the sum from n equals 1 to infinity of, ends up being -1 to the n over 2n. And what do we know about that?
Alternates.
An alternating series, and it converges, right, by the alternating series test. If you look at, we've looked at that one a few times today. You should already know that that converges by the alternating series test. But this is not all positive terms. So we also have to do the absolute value here. Which ends up being what series? The one that we had up above, 1/2n, which we once again know diverges by the p-series test. And so we've now checked our endpoints. We've checked our interval and radius of convergence. And we should now be able to say that our radius of convergence is 1, that this converges absolutely. Where does this converge absolutely? From 2 to 4, right? That it converges conditionally on what interval? I guess just specifically at x equals 2, right? And that it just converges on the interval 2 to 4 on the 2, but non-inclusive on the 4. Good or no? Cool. All right. Yeah, and Shayla, I'll go back and look at the previous one. So for this one, right, if you end up with absolute value of x minus a from your ratio test, and you got to put it less than 1 to see when it converges, your radius of convergence is going to be 1. Way back, I don't know, let me see. I think it was in here. Yeah, right here. Your interval of convergence is this absolute. This is where it diverges, but absolute value of x minus a greater than r is where it diverges. So absolute value of x minus a is less than r is where it converges, and r is that that value for your radius of convergence. So if you end up with this inequality, absolute value of x minus a is less than r, which is effectively what we got here, right? We found this interval, right? This would be absolute value of x minus 0 is less than 1, gave us a radius of convergence of 1. This one, because the limit came out to be 0, we know that the radius of convergence, just for the ratio test, it told us that the radius of convergence was infinity, because this thing converges for all values of x. For this one, we got infinity for our limit using the ratio test, except at -1, which means that this only converges at this one specific value, which tells us that the radius of convergence is just 0 because there's no interval of convergence. There's just a single point at which it converges. And then this last one, we got this same inequality, absolute value of x minus a is less than 1. So 1 is our interval of convergence. Suppose I'd have like a 4 down here though, instead of a 2 down here. Then I'd have x minus 3 over 2 as my limit. 2 would get multiplied up here, and I'd have absolute value of x minus 3 is less than 2. My radius of convergence would be 2. And we'd be going from 5 to 1 instead of from 2 to 4. Does that make sense, Shayla and everybody? Yeah. Okay. Cool. Gosh, I know we're over again. There was one other small thing I wanted to talk about that's not really required for the AP test, but is a good test to know, called the Nth Root Test. So we'll just briefly touch on that on Monday. And the only other thing I wanted to do is, this is up in the notes, so you should be able to look at this, but this is, I just stole this from one of the textbooks. This is sort of the order you might want to go through when you're trying to determine if things converge. So this is up in the notes in the Google Drive. But it just kind of says, all right, take a look at the nth term test and the geometric series test and a p-series test, and then so on and so on, until you can figure it out. And the only thing that's on here is this thing called the nth root test that we haven't talked about. Everything else we should have talked about. And I will, like I said, briefly touch on that, even though it's not required for the AP test. It's a cool little test that works out nicely. So yeah, consult more advanced books. Exactly. So I can't remember if I stole this. I don't think I took this from your textbook that you're supposed to get. I think I took it from a different, much better calculus textbook that I sometimes use. But yeah, that's good. Consult more advanced books or explore with a computer. So that's that.